Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on Cauchy's integral theorem. So, coming to the actual theorem statement, let us consider a function f of z which is in the form of f of z which is in the form of u plus iv, where u and v are two functions of x and y, which is an analytic function on and within a simple closed contour C, and let its derivatives are continuous there. Then, according to Cauchy's integral theorem, the line integral of this f of z dz along that curve C is 0. So, the Cauchy's integral theorem states that if the function f is analytic on and within a closed contour C, that means a simple closed curve C, then the line integral along this curve C is 0. That means it vanishes. So, the Cauchy's integral theorem helps us to evaluate the line integral of a function of complex variables along a curve C. Now, when we can apply this theorem, first this f must be analytic everywhere on and within the closed curve C. Then only we can apply this Cauchy's integral theorem. And according to this theorem, the integral value is 0. That means the line integral vanishes. Now here we can consider some examples. Here C is the boundary of the square with vertices at the points z equal to 0, z equal to 1, z equal to 1 plus a and z equal to I, where f of z is 3z plus 1. Now first of all, it depends on the function f of z and also the curve C. Here the function f of z equal to 3z plus 1 is analytic everywhere. That means on the entire complex plane. So this is analytic on and within the given square with the given vertices. Hence we can apply Cauchy's theorem and the result will be 0. The integral f of z dz is 0. Similarly, if you consider a function like sin z, cos 3z, e power 2z, z square plus 8, all these are analytic everywhere. So, on and within a given curve C, these functions are analytic, hence the line integral vanishes, is equal to 0. So, these are some examples on Cauchy's integral theorem. Now, let us solve some problem. Consider the region 1 less than or equal to mod z less than or equal to 2. If capital B is the positively oriented boundary of this region, show that the line integral of this is equal to 0. So here, given f of z, what is the function here? 1 by z square into z square plus 16, and the region C or the B, capital B, is 1 less than or equal to mod z less than or equal to 2. So this is the given region. Now here this region is covered by mod z equal to 1 and mod z equal to 2, and these are mod z equal to 1 and mod z equal to 2 are circles with center at origin and radius equal to 1 and 2 respectively. So the first one is a circle with radius 1. So we can draw that, a circle with radius 1. And second, mod z equal to 2 is another circle with radius 2. Now B is the region. Here the shaded region. This is the region B. So the first one, the inner circle with origin, center at origin and radius equal to 1, and the outer circle is the center at circle with center at origin and radius equal to 2. And we need to evaluate this line integral over this shaded region. Now, first of all, by Cauchy's integral theorem, if f of z is analytic on and within a closed curve C, then the line integral vanishes. That means if f of z is analytic at all the points on the circle and within the circle. For example, if there is a point at which the function is not analytic, if the function is not analytic, then you cannot apply this Cauchy's integral theorem. And here such a point is known as singular point. Singular point. So first we check the singularity of the given function. That means the point at which the function is failed to be analytic. The function failed to be analytic. That means ceases to be analytic. So first we find out those singular points and then check whether those singular points lie with on the circle, on the curve or within the curve. If the point is outside the curve, there is no problem. We can apply the Cauchy's integral theorem. For example, if the singular point is inside the curve, then we cannot apply Cauchy's integral theorem. Since the statement is if f is analytic at each and every point on the circle and within the circle or on a curve and within a curve, then only we can apply Cauchy's integral theorem. So if the singular point lies inside the curve or on the curve, we cannot apply the theorem. So here to apply the Cauchy's integral theorem or to evaluate the given integral, first we need to identify the singular points, then check whether those singular points lie inside the curve or outside the curve. That is the main point here. So the given function f of z is 1 by z square into z square plus 1 plus 16. Now this function fails to be analytic at the points, so at the singular points. And how to find the singular points? Equate the denominator to 0. So the denominator is z square into z square plus 16. So that is equal to 0. So either z square is 0 or z square plus 16 is 0. So z equal to 0 or z square is minus 16. So z is plus or minus 4i. So therefore the singular points are z equal to 0, plus 4i and minus 4i. And here the region of integration is bounded by two circles. One is a unit circle and the other is a circle with radius 2. So this is the shaded region in which the radius lies between 1 and 2. But here one of the singular points is z equal to 0 and the other are 4i and minus 4i. So it is very clear that these singular points lies outside the region, outside the shaded region, capital B. So therefore, by Cauchy's integral theorem, line integral C f of z dz is 0. So that implies here these points lie outside the region. So therefore f is analytic everywhere, analytic on and within the region B. So f is analytic on and within the region B, hence we can apply Cauchy's theorem, and according to Cauchy's theorem the line integral vanishes, hence integral 1 by z square z square plus 16 dz is 0. Similarly, let us consider another problem. Evaluate the line integral where C is the circle mod z equal to 1, which is unit circle with center at origin and radius equal to 1. So here, what is the function f of z? E power 2z by z minus 2, and the circle is mod z equal to 1 is a circle. It is a circle. It is a circle with center at origin and radius is equal to 1. And here, to find the singular points, how to find the singular points? How can we find or identify the singular points? By equating the denominator to 0. So this part, z minus 2 equal to 0, that implies z equal to 2. So the given C is a unit circle with radius r equal to 1. But here the point z equal to 2 lies outside this circle. So clearly z equal to 2 lies outside the given circle C. Therefore, F is analytic on and within the curve C. By Cauchy's integral theorem, line integral C f of z dz is 0. So line integral e power 2z by z minus 2 dz is equal to 0. So to evaluate the line integral, first identify the singular points of the function and then check whether the singular point lies on the curve or within the curve or outside the curve. If the singular point lies outside the curve, we can apply Cauchy's integral theorem. If the singular point lies on the curve or within the curve, then we cannot apply the theorem, and that can be evaluated using some other method. Similarly, here it is required to evaluate the line integral z square minus z plus 1 by z minus 1, where C is the circle mod z equal to 1 by 2. So here the function f of z is z square minus z plus 1 by z minus 1, and the circle is a circle with center at origin and radius equal to 1 by 2, that is 0.5. Now how to find the singular points of this function? By equating the denominator to 0. So the singular points can be identified by equating the denominator to 0. So z equal to 1, and here the radius is half, 0.5, and this point z equal to 1 lies outside that circle. So here z equal to 1 lies outside the given circle C. Therefore, F is analytic everywhere or analytic on and within the given curve C. Hence, by Cauchy's integral theorem, the line integral f of z dz along the curve C is 0. So here the given z square minus z plus 1 by z minus 1 dz will be 0, since this point lies outside the circle and f is everywhere analytic on and within the circle. Similarly, there is another example. Here B is the positively oriented boundary of the region between the circles mod z equal to 4 and squares with sides along the lines x equal to plus or minus 1 and y equal to plus or minus 1. So here the sides of the squares are x equal to plus or minus 1 and y equal to plus or minus 1. So we can consider the square here and then outside a circle. So B is the positively oriented boundary of the region between these two. So this shaded region, this is the region B. We need to evaluate the line integral over this region B. Now here there are two problems. The first one is f of z equal to 1 by 3 z square plus 1. Now to apply Cauchy's integral theorem, first the function must be analytic on and within the given region. So first we try to find the singular points. And how to find the singular points? By equating the denominator to 0. 3z square plus 1 is 0. So 3z square is minus 1 and hence z square is minus 1 by 3. Therefore z is plus or minus under root minus 1 by 3. So I by root 3. And here it is very clear that this z equal to plus or minus I by 3. So since z equal to plus or minus I by 3, these points lies inside the given square. Since the square is bounded by x plus or minus 1 and y plus or minus 1, and here our values points z equal to plus or minus I by root 3. So those points lies inside the given square. But here we need to evaluate the region, line integral over this region B. So that implies f is analytic on and within the region P. So by Cauchy's integral theorem along over the region B, the given f of z dz is 0. So that implies 1 by 3 z square plus 1 dz is 0. So that is for the first problem. Now similarly there is another problem. F of z is z plus 2 by, the second one, f of z is z plus 2 by sin z by 2. And again here the region is bounded by a circle and a square. So the region is, there is a square and outside there is a circle. So in this region we need to evaluate the line integral. Here again to find the singular points, equate the denominator to 0. Sin z by 2 is 0. Now when the sine function vanishes, when the angle is plus or minus n pi. So z by 2, when the angle is plus or minus n pi, hence sine plus or minus n pi. So z by 2 is plus or minus n pi. So z is plus or minus 2 n pi. Therefore the singular points are z equal to 0, z equal to plus or minus pi, z equal to plus or minus 2 pi, and so on. And here the point z equal to 0 lies inside the square, whereas the remaining, all the remaining points lies outside the circle. So here the first point lies inside the square and the remaining plus or minus pi, plus or minus 2 pi, 3 pi and so on all lies outside the circle. Hence the function is analytic. Therefore the function f of z is analytic on the region B. Therefore by Cauchy's integral theorem, the line integral f of z dz will be 0 and hence the line integral z plus 2 by sin z by 2 over the region B dz is 0. So the Cauchy's integral theorem helps us in evaluating the integral of a function of complex variable. Now, in today's session, we have solved some problems on Cauchy's integral theorem, and according to Cauchy's integral theorem, integral f of z dz, the line integral along C is 0 if f is analytic on and within the closed curve C. And here, to apply Cauchy's integral theorem, first we need to identify the singular points and then check whether those singular points lies inside the circle or outside the circle. Based on that, we can apply the Cauchy's integral theorem, and Cauchy's integral theorem helps us in evaluating the line integral of a function of complex variable in a simple manner. So, this is for the today's session, and we will meet in the next session.